Good afternoon. I only reached England a few months ago, but I can say that I'm amazed by the speed of the internet and the immediacy of content. And I guess I'm like many South Africans that travel to Europe or the US, and they feel the same way. And then they come back to South Africa, and they criticize local network providers for poor speeds. Unlike them, though, I understand that the quality of the networks in South Africa have nothing to do with the speed of the internet. And by the end of this presentation, if you don't already, you'll understand that too. So today we're going to talk about the evolution of networking, and we're going to talk about global application optimization. And to do that, we need to discuss a few other things. We're going to talk about the internet and how it's becoming a go-to service and infrastructure for application delivery. But what's holding people back, and does it really perform at the right levels? We're going to talk about CDN networks and why I don't believe they're best positioned to deliver business-critical applications for the enterprise. We're also going to talk about latency and what it's doing to your user experience. And my personal favorite, the impending death of MPLS. But all this really comes down to one thing, the evolution and revolution that is global infrastructure and software as a service. So let's talk about latency. Latency is the measure of delay between an action and a response, or in this context, between the user and an application. It's made up of things inside the network like distance or network propagation. It's also made up of things like routers and amplifiers and repeaters. And as your data passes through them, it creates some form of delay. And of course, it's caused by congestion. Now, before we can talk about latency more, we also have to understand the TCP/IP protocol. As its name implies, the Transfer Control Protocol is responsible for transferring data over IP networks in a reliable and predictable manner. And it's also a connection-based technology. And as a result, every time it sends data across the network, it needs a response or acknowledgement back from the network to say that that data has actually been sent. And when it sees that response, it looks at information in the response, and it does something that's very, very key in this discussion, which is it establishes the TCP/IP window size, or more importantly, the amount of bandwidth that your user will get when he accesses an application. So what I'm going to do is I'm going to use examples in terms of how this happens as we introduce latency into normal networks. And to do that, I'm going to use this graph. On the horizontal axis, we have latency. On the vertical axis, we have bandwidth. We have the user and the application, and then supporting that is the TCP/IP protocol. Now, the calculation that the TCP window does is an actual calculation. It's taking a standard 64 kilobyte window, dividing it into bits, and then dividing it by latency. And that gives you the maximum theoretical bandwidth that your user can get to engage with that application. We're also going to make some assumptions, and the assumptions are that there's only one user in this network. He has 100 megabits of dedicated premium MPLS bandwidth at his disposal, and there's absolutely no congestion or packet loss within the network. So we're going to start by putting the application 5 milliseconds away from the network, which for people in Cape Town, if your head office chair, is pretty much the speed that your regional users in Cape Town will access an application, whether it's in your own DC or whether it's in a DC in Cape Town as an extension of your MPLS network. If we do the calculation, we get 102 megabits per second maximum theoretical bandwidth size, which means that your user will get 100 megabits per second to access the application in real time. And as a result, it's going to be incredibly fast. But let's take the application and move it 30 milliseconds away. Or better yet, let's use the example that your user has now moved to Cape Town or Durban, which is typically around 30 to 40 milliseconds greater than Johannesburg or Cape Town, and see the difference that actually occurs. If we take the same calculation, right, dividing 512,000 bits now by 30 milliseconds, the maximum theoretical window size is 17 megabits per second. So your user has already lost 85% of his available bandwidth just by virtue of 25 milliseconds additional in the network. And as a consequence, his user experience has decreased considerably. Now, if we then take the application into a global infrastructure environment, such as Azure or AWS or Microsoft 365, and we do the same calculation, that same user, without anything else changing in the network, can now only get 2.5 megabits per second out of 100 megabits of bandwidth. Obviously, if you add in congestion, which you normally have in a network, you add in your link size, which is probably not 100 megabits per second, you'll realize the problem is pretty big. And this is the experience that your users have as you move into global infrastructure. Now, to resolve this problem, organizations like Microsoft and Amazon have got together with organizations like EOH at a carrier level and many others around the world to build an architecture to resolve the user experience problem. And they came up with products like ExpressRoute or Direct Connect. And what they do is they guarantee the underlying network, and they create this MPLS delivery mechanism into these cloud services. But what this shows you is even though it's great to guarantee the network, and even though you can get an extra 20 milliseconds of efficiency out of that network, your issue remains largely the same, because in an express route environment, you're going to get a maximum of 2.8 megabits per second in the same physical network, because 180 milliseconds is still in that network, and that's the minimum you're going to get managed and balanced over 3 cable systems outside of South Africa. So what we also want to just quickly touch on is packet loss. Now, the reason people buy MPLS networks is because there's 0% packet loss, but I'm not sure if anyone really understands why that's so important. So what I'm going to do is I'm going to show you using that same user who's got 100 megs of bandwidth, his application's sitting overseas, but now he's accessing it over the internet. Now, the internet is always susceptible to some level of packet loss, whether it's 0.1% or whether it's 1.5%. And the further the internet is, or the further the application is over the internet, the more likely you are to encounter packet loss. So what happens if we introduce 1% of packet loss into the same network? You reduce the user's bandwidth by a further 68%. Now, this means that whilst internet is practically the best delivery mechanism for global application delivery at a cloud level, because it's susceptible to both latency and packet loss, it has a very big undermining effect to the user experience. So just a quick catch up on that. More latency equals considerably less bandwidth. MPLS networks, like ExpressRoute, improve delivery by reducing latency slightly and by ensuring that there's no packet loss, but not enough to overcome the serious problem of latency over long-distance networks. And internet access is susceptible to both latency and packet loss, which there generally is in the internet networks. So let's understand CDN networks. CDN networks have been around for a very long time, and they've had a very, very good function for operators and users alike. And really what happened is, a couple of years ago, companies like Limelight and Level 3 realized there's a commercial business model in taking information and keeping a duplicate information, or keeping I can't believe I forgot that, keeping a copy of that information locally inside a local infrastructure architecture. So to do that, they built big caching platforms, and they put them in countries like South Africa. And every time a user wanted to go and access information, that information would be stored locally in that cache, as opposed to having to go to the source to get that information. And this really just comes down to latency again. If you went to source, it would take them 250 milliseconds, the window size would be low, and the experience would be poor. Now that the actual software is sitting locally, the window size is large, and the user experience is good. And of course, it's saving the network operator millions and millions of dollars of global bandwidth and resources. As a result of its success over the last 10 or 15 years, enterprise companies are approaching CDN providers to help them deliver global applications. But for me, that's a bit of a problem. The reason for that is because the historical and still today current infrastructure that CDN providers use to deliver their CDN content and to synchronize their caches around the world is the lowest form of internet. It's best effort internet, because that actually works from a synchronization point of view, and it makes economic sense. And as you know already, internet has high packet loss, and internet has high latency, so when you apply that to business-critical application delivery, you have a problem. And of course, their success has been around caching and making static content available. But applications in the enterprise space are dynamic, they're real-time, and a large amount of them are simply not cacheable. And lastly, we're going to talk about optimization software. Optimization software has been around for a lot of years, but I think in the next couple of years, optimization is going to be adopted by more and more organizations to resolve the key element around application delivery. So most of the time, you recognize optimization as compression, caching, application control, and delivery. And in the background of that, there's been a service or a technology called TCP/IP acceleration. It's always been in the background because most of the time that organizations roll these services out in domestic networks, latency isn't the biggest issue. But as latency becomes a bigger issue, it becomes the most important element of this software. So we're going to use the same example to talk about what TCP/IP acceleration is and does in order to resolve the issue of latency. And a lot of people argue you can't resolve the issue of latency because it's about physical distance. The fact is we're not trying to resolve latency. We're not trying to reduce latency. We're trying to change the way the TCP/IP protocol looks at latency to determine how much bandwidth the user will get when accessing the application. So we're going to go back to the same example. We have a user. We have an application. It's 200 milliseconds away. You already know he's lost 97.5% of his bandwidth. He's got 2.5 megabits per second left. And we also know that when the TCP protocol sends information, it requires a receipt. When it looks at the receipt, it sees that it took 200 milliseconds to receive that receipt, and it does that calculation. So what we do to resolve that is we put technology just in front of the user and just in front of the application on either side of the network. And what this technology does is it responds to the TCP protocol without the packets having to go all the way to the destination. In this case, this device or this technology is responding within 5 milliseconds. And the result of which is that the calculation goes back to the maximum theoretical window size of 102 megabits per second, even though the application is sitting 200 milliseconds away. And as a consequence, can provide up to 40 times higher bandwidth speeds because you can actually use the physical network and you've overcome the latency issue. So just to recap quickly, CDN networks are based on best effort internet, and as a consequence, for me, they are not ideal for business critical application delivery. TCP/IP acceleration is the key to application delivery and is the key to resolving user experience going forward into the future. So now that we've created some context, let's talk about the evolution of networking. This probably represents the design that most organizations still have today, which is a standard national or global MPLS network. And it's characterized by all your applications sitting in your data center or in a data center near your head office as an extension of your physical network or your MPLS network. And you probably recognize some things that you have a user who's sitting in Johannesburg next to the data center in 5 milliseconds, and he thinks the network's fantastic. You have your user that's sitting on the MPLS network in Cape Town or Durban, and he's not as happy as the user in Johannesburg. And then you open a branch in Australia, and they're using the applications in Johannesburg, and those users think you have absolutely no idea what you're doing, because you're trying to get to that application in 300 milliseconds, and the results are terrible. Another thing that characterizes this network is that you're actually backhauling the internet yourself in the network. You're backhauling it from a single aggregation point to all the different regions and to all the different users. And that's fine as long as the internet remains small, and as long as the applications coming from the internet are not business critical. But of course, that's all changing. And what's exacerbating that issue is the fact that we have things like BYOD, which has brought in thousands of devices into the organization, supported by fantastic advancements into wireless, where you can walk in and your device automatically synchronizes the latest version of iOS. You've got consumerization of IT that is driving IT to develop services for consumers as opposed to just the organization. You have unified communications, which of course allows your users to communicate on so many more levels than they did before. And you have this massive content explosion. And all of these things together are creating a very, very big question mark as to whether MPLS is the right architecture to move into the future. So that's why I call it the soon-to-be-past network. And so we're going to look at today's network design. Today, the most logical network design that people are using or rolling out is the hybrid network. And the hybrid network is a simple design change. You're simply allowing your branches to connect directly to the internet as opposed to having to go through a single aggregation point. And why not? Your applications are starting to come from the internet, and it makes sense at an economic level and a technical level. Economically, you're saving all your MPLS bandwidth because you're not backhauling internet. Technically, there's less latency going from internet directly to the user because you're not going through the MPLS network. And as a consequence, your user experience would be better. But of course, you can't do this by trying to manage an MPLS network and an internet network separately. You have to have some form of intelligence that overlays this network that allows you to do that. And that's where we start moving into the software-defined networking space, which to a large degree is still driven and delivered by hardware, but is software-defined by nature. And what the software-defined networking space allows you to do is look at the network agnostically. It can look at the network and the resources, and it can make really intelligent decisions on behalf of the application, which you couldn't get in the MPLS network. Some of those things might be basic things like MPLS offload, where if you have a failure in your MPLS network, these technologies will help you build an IPsec tunnel through the internet to deliver your application back to the head office, which is great. Other things which are even more exciting is something called dynamic link selection, where the technology looks at the application, it looks at the requirement of the application in terms of the network, like latency and packet loss and JIT and availability, and it looks at the available links, and it chooses the best link to send that data at any point in time. Even if it means that when the MPLS network is working fine, it'll send your business critical application over the internet. And we're seeing that happen more and more in domestic networks because there's more available bandwidth in the internet. The latency in domestic networks is pretty low, and as a consequence, so is packet loss. And the available bandwidth in TCP window size is considerably higher. But here's where the problem starts. What you've done now is you've moved your SharePoint and Exchange 200 milliseconds away. And you start having really large user experience issues for the users that are accessing those applications because they've lost 97% of the available bandwidth to access them. And of course, this issue starts to become bigger and bigger because of the way organizations try to resolve them in the manner that they've developed these networks. So let me give you an example. So you have your MPLS network, you have your internet breakout. Customers may be using Salesforce.com in Ireland or the States. They're doing some of their dev work in AWS, and they've rolled out SharePoint and Exchange. And this is a very good example of a lot of large organizations in South Africa. They've got their overlay network, and they've realized that going through this network design and using the internet as a basis for application delivery is not working because packet loss is high and because latency is high over the internet. So the knee-jerk reaction, of course, is to try and extend the same optimization and intelligence into the cloud environment. So they spin up devices in front of each cloud environment, or they put down physical devices, and then they realize those devices actually can't talk back to the network because they're not built to live on the internet, they're actually built to live in private networks. So you have to put down firewalls, and it starts to become very, very complex. And they start building IPsec tunnels to manage this, which is fine if it worked. But at the end of the day, because the internet is erratic, and because it still suffers from latency, and because it still suffers from packet loss, you get highly inconsistent application delivery, which still frustrates the users to the same degree it did before. So the simple reaction at that point is to revert back to what you know, which is a low latency, zero packet loss, premium MPLS network. So organizations go back and start deploying ExpressRoute and AWS Direct Connect as an extension of the MPLS network with the optimization. And you know what? It works a lot better. But the cost elements around this are considerable. And the whole principle around MPLS networks, as we've already seen, doesn't support the whole basis and the whole benefit that you get from cloud architectures today. And of course, this environment just simply doesn't benefit or support web applications. Once you add in all this complexity and all this cost, I think for a lot of organizations, if they had realized it would revert to this, they may not have actually moved into the cloud environment in the first place, which is an unfortunate thing. It's a very expensive and very, very complex exercise. So just to recap on that, traditional MPLS networks can't economically or dynamically support networks in today's content and application economy. Hybrid networks bring together the best of the internet and MPLS to assist in addressing the requirements and opportunities companies see today in leveraging cloud. And when you move into cloud, though, you hit a wall because you just cannot get the performance and the delivery that you need over a long latency and packet loss network. So let's talk about the future of networking. Okay. So if I had to come to you and you knew all this information, you've had all these experiences, you knew the good and bad about everything that's happened over the last couple of years, and I offered you $5 billion to build a network that would best service your requirements, what would you do? How would you build it? Well, for me personally, I believe that every single one of the applications your organizations consume in the future will come from cloud, without any exceptions. And as a result of that belief, I believe that I would start building that network with cloud as a center point, not as an afterthought, not as an extension, but as the key central element of this network. And not just any part of cloud, every part of cloud. Every infrastructure as a service provider on every continent, every software as a service provider, and every platform as a service provider. Now, also what we know through what we've been through is that in order to deliver these applications at the highest level, we need a network that has low latency and has very low to zero packet loss. And the best network to do that, of course, is MPLS again. So I would build a global core MPLS network. Now, everyone's saying, well, this is starting to look pretty much like where we are today, but there are some exceptions, and let's talk about them. The first one is that all the intelligence that we're creating in these overlay networks is now embedded in this network. In other words, this network comes with all the features of TCP/IP acceleration, caching, deduplication as part of the POPs and as part of the core network, which means that when you buy an application on this network, it comes fully optimized, and you get the best experience you can possibly get without having the complexity of adding technology or high CapEx fees or high management fees. The other thing that really differentiates this network is that you're going to access it from the internet. Now, we've gone from a soon-to-be-passed network, which is primarily MPLS, to a hybrid network, which is a balance between MPLS and internet, and now I'm talking about an internet network, where you engage with it directly from the internet. And MPLS in this regard is only there to support the underlying network and application delivery. You do not engage with this network as MPLS. It's no longer MPLS for you. And as a consequence, technologies like IPsec, which are starting to evolve and become more commonplace, are becoming the center point of these types of networks. So I'm going to give you an example of what that would look like. We're going to go back to the same customer example. You have the Johannesburg and now the Australia branch. And the first thing you'll notice, there's absolutely no applications in their network. Because all the applications that they were accessing are now available directly from the source, directly from the physical network. So when your user accesses the web, it's a default access, default internet access. So he goes straight there. But when the user wants to access something like voice or Citrix, the network has enough underlying intelligence to identify that traffic, offload it immediately as fast as it can within a couple of milliseconds to a premium, low latency, zero packet loss network and deliver that globally with TCP/IP acceleration to overcome the latency issue. If you take the same type of environment and you add it to things like web-based services, then what you're doing is you're just breaking out of this type of network to the internet on the other side. But because you've tightly integrated these services and infrastructures and POPs into the data centers that deliver your cloud infrastructure, technically it's not even going out to the internet. So you can limit and control the effect of general internet access, which in this case would be almost zero. And lastly, the only thing that you're really going to do from a network perspective, from branch to branch, is probably things like voice. Sound far-fetched? Sound impossible? Well, it shouldn't be, because there are thousands of customers that are already being delivered services on networks like this. So let's talk about some of the benefits of those networks. Firstly, in principle, you bring your own internet link. Internet is one of the most pervasive technologies in the market. Everyone has one. And in this case, that's all you actually require. And as a result of the fact that this is a software-defined network, it's not defined by physical architecture, it's not buying an MPLS link that you have to wait 3 months to install and you have to sign a 12-month contract before you even know that it works. This is rolled out in hours or days because it's just about launching an IPsec tunnel from a router to a router because it's software-based. And as a consequence, you can actually go through a process of delivering an entire global WAN within 7 to 14 days because of that element. That, to me, is one of the key benefits of the software-defined networking space and the software-defined WAN space. Because what the network does, all it wants to see is what IP addresses you're accessing, what URLs you're accessing, and it has enough intelligence within the network to find them at their source, pre-optimize them, and send them back. The result of that, though, is you can actually get 40 times faster application performance. And it's a calculation. It's not a thumbsuck. It's not something we invented. It's an actual calculation around how the TCP/IP window works. And if you combine that with low latency, embedded optimization, and 0% packet loss, the efficiency and the benefits that you can get out of networks like this are considerable. And on a global level, the performance that we see against things like MPLS are large because of the fact that everything else is already tightly integrated into this network. And as a consequence, it has a significant TCO benefit because you're taking all the complexity and all the management that you've traditionally seen in these networks out. So these are some of the companies at a global level that are actually leveraging architectures like this. Now, these are the kind of companies that are delivering them. So today, we have a growing amount of global software-defined providers. And what's interesting about them is that if you really understand and believe in this type of evolution, then you'll believe that the likelihood of you buying your next network from a company that you've heard of today or never heard of before that actually doesn't own any physical infrastructure or fiber, you'll realize that in this scenario is very likely. Just in the same way Uber revolutionized the whole taxi industry just with the software app, this principally has the same type of concept, obviously, not as simple as that. So today we have organizations like Ariaka, VeloCloud, Acedo, and you'll see, based on who's buying these companies and investing in them, that these companies are playing a significant role. So companies like Cisco, Riverbed has bought Acedo, KDDI rolling out about 250 POPs worldwide with Ariaka. The only one company that differs to the rest is Ariaka, because that network that I showed you just now is what they actually built globally over the last 10 years. And it is a very unique, very, very powerful infrastructure. And it is the difference between any other service that leverages the internet because it has 0% packet loss and very, very low latency. So in conclusion, over the last couple of years, we've seen amazing technology like Riverbed and Ipanema that's helped organizations correlate application access and delivery to the network. The problem that I find they're challenged with today is in the cloud environment, which typically relies on internet access, they're struggling with the latency and the packet loss elements and are struggling to provide the same performance they did in MPLS networks. So in MPLS networks, they work very well. Migrating and evolving into hybrid networks has actually started to become quite challenging. You've got CDN networks that have come from the internet, and are struggling to provide business-critical applications because the internet suffers the same issues as it does, as we've explained already. And if they want to succeed in this market, they're probably going to have to build dedicated, guaranteed infrastructure underneath, which of course would completely undermine their business model in CDN delivery. And then you've got this new range of organizations in the software-defined space that are taking the best of the internet and the best of MPLS networks and a very intelligent embedded software within their network and delivering capability that's something that I haven't seen for a very, very long time. So my predictions, none of the companies you buy optimization telecommunications from today will most likely be your suppliers in the future. Like many disruptors in many industries, they are not limited by history, their networks, or by protecting revenue. And for me, software-defined networks introduce something the market needs but does not understand yet: simplicity, efficiency, speed, and economics. Thank you. Are there any questions? No. Okay. Okay.
You had one of your example companies using this technology for outreach instead of government. The one that came to mind was GoPro.
Yes.
GoPro is a very successful marketing company, and it's also a very successful video manufacturing company. Where are they using these networks?
Well,
How are they using networks?
Well, look, GoPro is still an organization at the end of the day. So they have branches, they have distribution channels, you know, they have offices in tens, if not hundreds of countries around the world. And they use these networks to replace traditional networks, like traditional IP-based VPNs or traditional MPLS networks. Because like many networks, even though those networks have serviced them in the past, as they try and centralize applications into global cloud infrastructures, they start to see more and more application issues and delivery in outlying regions. So some of these organizations have converted their entire networks onto infrastructures that are what I've explained today. Other networks, however, are looking at areas where they have real problems. So we've worked with companies that have a 100-site network, but they only have one branch in China that is struggling with application delivery from a cloud perspective. And they leverage these services just to resolve that one problem. So there's a vast way that organizations are using this today, from an all-in strategy to just resolving certain pain points in their own network infrastructures. Anything else? Yes.
Yes, I'm Daniel from Grading. We provide software as a service. I actually want us to look at, my question is looking at it from the other side. So now we have infrastructure sitting in Amazon Web Services in Ireland, and most of our customers sit here in Cape Town and Johannesburg. So obviously there's a bit of latency, between those two areas. Would you guys also be able to help us as the software as a service provider, to reduce that latency, or does the onus still lie with, say, some of the companies that use our infrastructure, like Discovery or MWeb or whoever?
So to answer that, to me, there's a couple of things you could or should be looking at. I think the one I explained earlier, which was CDNs, which help organizations publish content at the edge of the world, in other words. So what I'm hearing is that your application that your users or your clients access is actually sitting in Ireland, and they're probably the ones experiencing some application access problems. So there's two ways you can do that. You can either look at the CDN element to try and publish that if enough of it is static.
See, that's the problem. We've already tried that.
Yes.
Yes.
Yes. So what Ariaka did is they rolled out their global network. And they realized, of course, that they had something unique in the fact that they controlled the physical network. And they had these caching engines which sat as a natural element of the optimization stack. And so they allow organizations like you to publish your application to the public. And the difference between them and something like a CDN provider is, number one, they're doing optimization on both sides. So they have TCP/IP acceleration, which CDNs don't have. And that's the killer here. And the second is they have a guaranteed underlying network, which, of course, then just allows the application to perform even more. So to me, the publishing of content is relevant. You either have to look at CDNs or you have to look at Ariaka for CDN access. You've already looked at the one, you might want to look at the other.
And then would we be able to deal, for instance, just us as Grading with Ariaka to improve that?
Well, the nice thing about software-defined networks, as I mentioned earlier, is that you don't have to make a serious commitment and only find out the results a couple of months later. And so because it's software-defined, you can actually roll out a POC in a couple of days, and you can measure the results with yourself and with your clients. And on the basis of seeing those results, you can actually make decisions of whether that technology is going to work for you as an organization. But I can say that the results we see in that regard are very unique, very, very powerful, and to a large degree, change that experience from what is a global experience to almost like. But it's something that I don't like to talk about too much because I'd rather just get someone to try it as opposed to listening to the hype around it. Anyone else? Yes?
No, you don't want to talk about it, but can you have any kind of case study or just on that score?
Sure.
What kind of impact
Yeah.
client example, anything like that?
Okay. Well, I can give you some examples, but I'm not going to use client names because some of them are here today and I don't have permission to do that. But firstly, I think the best examples that we have to give are to work with organizations that have actual problems in application delivery. So we work with a lot of organizations that say we're moving into cloud and we anticipate this issue. And in that respect, we consult with them to kind of give them a view of what they can expect. But it's hard to sell you something if you haven't really experienced the problem, and none of these technologies are cheap. So for us, the best way to resolve issues is when they've actually already started. So for us, when we work with an organization that's already deployed services into AWS or into Azure, and they've already got application issues, we can very quickly show them how to resolve those issues or what the options are to resolve them. And as EOH as a group, we're not technology specific. I mean, we've got very, very good skills in Riverbed, Ipanema, Blue Coat, F5, Ariaka. So what we try and do is we try and fit the best technology based on the client's specific problems. I'll give you one example. We rolled out, we met with an organization that had some problems in development work around AWS. And they're here today, so they're probably going to laugh at me. But anyway, they had development problems in AWS. And when I was meeting with them to talk about how we could try and address it and resolve it, we also identified that they were running Salesforce.com and Microsoft 365 for email and for SharePoint. And we chatted about those, and they said, no, those are fine. So I said, but anyway, just can we put them into the same POC, just for fun, just to see what happens? And we established the POC in 11 days. So in principle, end-to-end optimization, end-to-end application delivery, because you don't need to change your network if it's software-defined. You can build an IPsec tunnel over your current internet service provider's network. It doesn't matter who's your internet service provider, and it doesn't matter who your MPLS provider is. It's a very non-intrusive service. And the day after we installed it, the MD phoned the project manager and said, what have you guys done? So he said, well, we're doing some work with EOH, and in that case, it was Ariaka. And they're doing some testing on this network. And he said, well, I want this guy in the next day. So they called me in before I moved to England. And he said to me, look, it's very simple. What's the price? Because they've got a very simple issue. The issue that they didn't even realize until someone could resolve it, which is a business process issue. Their Salesforce.com information wasn't being updated to the level of detail that they required. So their management reporting was out. Because every time a salesperson tried to get to that information and to try to update it, it was very slow and it was very cumbersome. And as a consequence, they just didn't put much effort into it. Worse than that, and exacerbating that, as part of that is a product called Informatica, which is a plugin for Salesforce.com that allows you to integrate with other applications, and that sits in the US. And part of their business process is to actually open, let's just say, a customer take-on document, which is taking 3 to 4 minutes to download while the customer's on the line. So for a salesperson, that was very frustrating. So the document open process went from 3.5 minutes to around 27 seconds. And the salespeople were excited because they could actually use Salesforce.com and were happy to engage with it. And for him, as an MD, that was the most important thing. And as a consequence of that work, as well as the work and the benefit that we got out of SharePoint, and in SharePoint we see some really big benefits because it's basic information, as well as the work we continue to do with AWS, those are the kind of things that we're seeing in the market, and those are the kind of successes that we see, as one example. Yes?
What level of customer side configuration did you have to do on the networks to get that set up to run?
So it depends on the technology, but an example with Ariaka, because it's a software-defined network, you don't actually have to put anything on the customer side. So on the one side, you cannot just ask the customer to build an IPsec tunnel from their network to the Ariaka network, as an example. But what we like to do is we like to put what we call the ANAP, the Arioca Network Access Point, into the network because it has some very intelligent DNS features. It also extends the TCP/IP acceleration and optimization into the LAN. And all you have to do that is you have to give it a public IP address, you have to be able to plug it into the firewall, you have to be able to give it its own subnet, and you have to be able to allow it to route out of that network. And what that device does then is when it sees the traffic, because you pass your DNS through it, when you see the traffic coming through of the specific applications and URLs that you want to send over that network, it'll pick them up, it'll build an IPsec tunnel to that Arioca POP, and it'll send just those applications. So it's very specific around application delivery. For some customers, we deliver one application on the entire network out of 100. And for other customers, we deliver 5. Just depends on where their problems lie.
So then in order to get that best experience of the site and the content being consumed, for instance, or the application, ideally you would want that config and preferably the device.
Ideally, yes. That is our first standard, yes. Yeah.
So how many Arioca POPs are there around the country?
Around the country, there's 1. Around the world, there's 22 on every continent and in every major city. And they're now building out into Cape Town, and they're building out into Africa. And, I mean, they have a very aggressive rollout. I mean, they've been doing this for 10 years, so it is a mature business model. But, you know, Africa has been an area that they haven't necessarily focused on. And so we're really excited to see that because in Africa, you not only have the issue of latency, but you have an incredibly high cost of bandwidth. And in South Africa, I think the bandwidth cost issue isn't a big issue anymore. It's the TCP/IP issue. It's the latency issue. But in Africa, it's both. And in Africa, if you can save 50 to 60% of your bandwidth, I mean, this technology will pay for itself 10 times over, easily. And so we're very excited to see them roll out in those environments as well. Is that it? Thanks, guys. Thanks very much for coming. Thank you.